Alright, we should be actually switching up to just to double check, make sure that the stream is actually seeing Firefox, a web browser, and not the logo. Looks like it is. Okay, so hi everyone, my name is Taro Omiya, game developer from Omiya Games. I make a lot of games at omiyagames.com. I should really update this website, but you can check out all the games that I make in this gigantic list of really wacky games that I am sure you'll be very fond of playing. Good, I delisted Everybody Plays Golf because that was a terrible game. Anyways, just to kind of give some quick context here, if you go to techvalleygamespace.com/learn, let me put that up on a notepad so that we can actually see this really large. techvalleygamespace.com/learn, and then presumably I can zoom in. Zoom in. Zoom in again. I don't have a mouse right now, so this is kind of hard to do. Okay, hopefully everyone can read that. Nope, nobody can read that. Give me a minute. Mouse, save us. Alright, I inserted a mouse. There we go. There we go. Okay, so yeah, techvalleygamespace.com/learn. There's a huge list of stuff on here. One of them is programming. Under programming basics, we have slides part 1 and part 2 that we did back when our old space existed. But yeah, this is one of the first few lessons we've done, first couple of lessons that we've done. The lesson for today, the lesson for today assumes that you have actually gone through, read through, and kind of understood what's going on behind this. Just for a quick basics, I do go over it in the intermediate programming parts, but if you want a quick and short of what these slides talk about, they say yes, learning programming is like learning a new language, and then it goes into depth about how to understand the words, the concepts, the grammatics, and the syntax of how to write a line in a programming language. In this case, C#, which happens to be what Unity uses as its primary form of programming. Without further ado, I'm going to close this. Yeah. I can close this too. This is what when you try to open Unity, this is what it kind of looks like. I ask that everyone, if you are following along, to open up a Unity project and start by clicking New. I already put it in a HG folder tutorial right here, but I'm just going to continue right here. I'm just going to call this programming lecture. And then say 2D. If you select 3D or 2D, it actually does not matter, but 2D is the least distracting, so that's what I'm going to choose. I'm going to leave everything else unchecked and just say create project. It's going to say hold on, doing a bunch of stuff. Hopefully it'll get back to speed. In the meantime, what I'll do is I will go over this real quick. Reviewing the basics of programming. This is kind of encapsulating the stuff that we've learned from part 1 and part 2 of programming basics. They are basically what each line is supposed to represent. These are what the lines each are supposed to represent, just making sure. Comments are basically any human readable notes that the computer completely ignores. They are represented by starting off with a line with 2 backslashes, or they also have a /* and then ends with a /*. For double backslash cases, so long as there's a new line right after it, then that means that that's the end of that comment, and therefore the end of anything that you need to be reading. If you put in a backslash star, it must end somewhere with a star backslash to end that comment. Variables. Variables are used to store and recall information. You declare them, as in like they exist, by saying what the type of that variable is, then the name of that variable, which has to start with either a lowercase or an uppercase letter, and then you just say that equals some value and it equals true is the way to basically declare and set a variable to a specific value. You can optionally, this last part where it says equals true is in fact optional. In that case, whatever the machine happens to feel like the bool needs to be as default is chosen. So it's often recommended to always say equals true so that you know what value it starts with anyways. But it's, like I said, it's strictly not necessary. It's a completely optional thing to add in. These are the different types that C# value types have, including the bool, int, floats, doubles, and strings. There are a couple more that we're not going to talk about, but long story short, they're not too important in programming basics. Bool, of course, the values can either be true or false, and that's it. Integers are any whole numbers, -1, 0, 1, 2, 3. So these can store basically any number. Floats and doubles contain decimals. So in this case, the var float right here contains the value 0.1, while the double contains 0.2. In this case, I'm going to be largely relying on floats because for video games, efficiency matters, and floats sacrifices granularity, like they sacrifice precision or accuracy in the name of less memory. But doubles take up double the memory as floats do, with the consequence of being far more accurate. So generally speaking, if you're making an application, software application where performance is not a big issue, then double is the better option. However, since we're using Unity, we're going to be using float because Unity basically expects floats. And then finally, string stores words, which all you have to declare a word is by simply pulling 2 quotation marks. And any text that appears between those quotation marks is considered a string, and thus a word. Operations are basically a lot like math operations. Any sort of action that is applied on numbers or variables to cause it to become bigger or smaller or whatever. In this case, I'm demonstrating by saying var int. We're declaring var int starting value as 1. And then we can say var int equals var int plus 3. What this will do, I mean, a lot of mathematicians will laugh at this because this is a patently false statement. But in programming language, this is perfectly acceptable because how the computer interprets this is it says, okay, var int needs to be set by whatever the right value is. What does the right set of information say? So order of operation dictates that it's going to go through the var int plus 3 operation first. Var int value is being recalled, which initial declaration was 1. So it says 1 plus 3 equals 4, and then finally sets that onto the variable var, and thus by the end of this, var int will be set to 4. By the way, single equals stands for set. As this comment demonstrates, double equals stands for compare. So in this case, we're checking to see if var int is actually 4 or not. If it is, this operation will return a true bool. Operations also exist for booleans as well. They exist as double ands or 2 pipes for ors. If we use a double and, then it does an and operation. It checks to see whether the left side of the operation and the right side of the operation are both true. If they are, it returns true. If either of them are false, then it returns false instead. So in this case, we initialize the var bool declaration as true. But in this case, at the end of the line, we say double and operation on false. And because the right side of that is false, as in one side of that operation is false, it sets var bool to false as well. Finally, conditionals. Conditionals are any filters where it takes in a boolean in between these two parentheses, and if those parentheses happens to be true, then it runs that. Otherwise, it goes to the next one if there are any lines afterwards. So in this case, it's checking to see whether this first if conditional is checking to see if var int is less than 1. If this operation returns true, then it will run any lines in between these two brackets. In this case, the line happens to be debug.log quotation mark less, which in the case of Unity, what happens with that is it prints the word less on the console. The console being this right here, which because of my layout, let me just do one thing real quick, save layout, Taro's layout. You can disregard that. What's more important is the fact that I switch it back to this default because this is probably the screen you're looking at. But yeah, this if you look at the tabs on the bottom here, it says project and then console. If you have any lines that says debug.log and then you pull in any text in the between, that'll get printed right here in this window. Else if is a conditional that runs in the scenario where the first if fails. So then it just checks to see what is next, else, and then it checks to see the condition. If var int is double equals to 1, then it says run the debug.log. And the final else statement is if all of these ifs and else ifs fail, then run the else statement instead. Arrays are basically a fixed size list. You declare them by saying what the size of that list array is supposed to be, and also what type of that array is supposed to be. And then you can set individual values by pulling in bracket index. So in this case, it's 0 index, so 0 is the first index, followed by 1, then 2. If you try to type in 3, you're going to get an index out of bounds error, so make sure that whatever number you're plugging in is within the size of that array. In this case, the array is the type of float, so we're just setting each of these values into float values. Recall that in C#, if you pull in F at the very end, that turns a decimal value into a float. Decimal values by default are doubles, which is a problem. So in this case, we're automatically setting it to floats instead. And here we are returning what the size of that array is by calling var array.length, and then what the contents of each of those array elements are. List is like an array, except its size is dynamic. You just have to call the add function, such as true and false right here, to be able to add new elements to that list rather than declaring the size of that list at the very beginning. So in this case, we are adding 2 items, the first one being true and the second one being true. But for the first element, we are deliberately modifying it to say that that should be set to false, so that when this returns, it's going to say var list.count is equal to 2, and then var list 0 will be false, and var list 1 will be true. Dictionary is basically a lot like a list, except the index is not set to a number like this, but rather any sort of value that you decide. The type is declared right here, string int. I should have mentioned the type of bool right here is declaring what the content of that list is. But anyways, dictionary, the first type indicates the type that's supposed to be indicated in the dictionary as keys, and then the integer part will be the values of that dictionary content. So in this case, the first value when we're adding it is set to 0, and then we're pulling that to 1, and then I change that back to it's supposed to be set to 0. But in this case, what I'm basically doing is writing out a word and then translating that into a value, integer value. So then when I go to here, var dictionary, notice that instead of taking a number, integer, it's taking in an actual word that in turn returns whatever that dictionary happens to be containing within that value. And loops. All right, so while loops is the most simplest one, while loops runs whatever is in between those two brackets for as long as the content within these parentheses remains true. So in this case, this is checking to see whether the integer variable index is less than array.length. Array.length, of course, is the size of 3. This is a second way of initializing an array, by the way. So there's 3 elements in here, thus this array length will be 3. Then what it does is it returns whatever the value is inside the array length based off the index value, and then increments the index by 1. For loops takes the similar idea of what while does, but allows you to just define it all in one line. It's basically just a helper function real quick. It takes in 2 semicolons, and in between those 2 semicolons, 3 lines. So in this case, the first parentheses declares that an integer index is equal to 0. It checks to see whether the index is less than the array length. And at the very end of that loop, it runs index equals index plus 1. So in other words, incrementing the index by 1 value. And basically, it does the same equivalent as this, except with basically less lines. And then for each is a simpler version of a for loop where the syntax is in between the parentheses right here, the type of the element, the name of a new variable to be created, in is a keyword, and then R is this variable right here, the array variable. So in this case, element will be set to each and every element inside the array. So inside the first loop, it'll be 1, then it'll be 2, then it'll be 3, and then that's what debug log will be printing on the console. And finally, functions. Functions is a list of lines. It's used for organizing a set of operations quickly, so that you can repeat using those lines using just the word of that function itself. So this is a good example. Check word takes in a parameter called word and returns an integer value. Then it has these couple of lines right here. It's also returning integer variable because they're the return type right here requires it to return some sort of integer. But anyways, it's going to go through here. It's checking to see what the word is. If it's not 0, then it chooses a random integer. Otherwise, if it is 0, then it sets var into 0, returns that. And then here we're actually using that function right here, check word parentheses, and then we're pulling in 0. This is how functions are being called. This is how it lets you reuse that same set of functions. So finally, we're past the basics. We're moving into intermediate programming. Fun stuff. This is part 1. I think on the description, I wrote something like we'll talk about inheritance. As I wrote it, I did not have the time to add in inheritance, so that'll be part of part 2. But we will still talk about, in general, we will still talk about some basic ideas of object-oriented programming, and we'll further go into more details on that in part 2. But anyways, part 1. So focus. Recall that in the basics, functions is a way of organizing a bunch of lines that you wrote. So when you went through like basics programming, what we basically taught you is being able to write out lines of code. So here I already have some bunch of stuff here. I'm going to create a new C# project. And in the meantime, whoops. If you expand Untitled and main camo, that kind of gives you a bunch of options inside the inspector. I'm going to go ahead and write up a test script here. I'm going to call that test struct. Oh, whoops. Oh yeah, new script. And then the new script, we're going to call that capital test struct. And then create and add. Nothing selected. If you double click on that, hypothetically speaking, that should open up Visual Studio, and this should be basically the code that you should be seeing. So when we were talking about earlier about coding, the idea has been largely like taking a bunch of lines and either creating new variables, so new var int equals 0, or creating operations using that integer variable. So integer var int plus 1, var int equals var int -1, and then finally debug.log whatever. Whoops. So then what a function would do is it allows you, this is actually a function right here, void start. What a function would do is it will basically let you take all these lines and organize it into a single label so that when I need to use it in another function, I just have to call start. And then that'll basically do exactly this over and over again. Basically, then what we're going to be talking about with intermediate programming is using this similar basically extending this idea with something called a struct, where we organize all of these lines even further together, with the idea that structs are basically a collection of variables and functions. So yeah, they're basically short for structures. It's worth noting that in Unity there are a couple of built-in structs that already exist. But structs are basically any custom variable type that you can define. Unity has already defined a couple that allows you to use as if it's just like any other variable, but what it does is it actually holds and collects a number of integer or a number of variables and functions into a single single variable that you can easily call and manipulate with. So the main purpose of it is just further organizing code like functions do. So a quick note about structs. It's a C# feature. Most languages do not have struct, and C++ technically has a feature named struct, but it acts nothing like C#. I'm starting off with struct in this case, even though it's like a very specific niche feature on C#, because quite frankly, it's a lot easier to talk about than it is about classes. So in this case, again, we're going to be largely talking about structs. Just to make sure, is everyone that is listening to the stream, are the volumes okay? Cool. So I already started making this test struct script, but what we actually want to do is we want to start creating a new struct here. So we're going to create a new struct, we're going to name it planet, and we're going to give it two variables, string name and acceleration. So without further ado, let's delete all this. This is going to be inserted right here below the line test struct. So I'm going to say this is a public, okay, public struct. You might notice that by typing Visual Studio's autocorrects, so feel free to take advantage of that feature. We're going to call this planet. And then, let's see, we want to create a public string name. String, as you might recall, is a word. And then public int, or float acceleration. Float, again, you might recall, is a decimal value. And then finally, we want to grab what the gravitational force is, which in this case is a function. Public float gravitational function. Gravitational force, int float mass. And who knows physics? With just acceleration, how can you solve the force? Sorry, I made this really easy for myself. Yeah, so in this case, this allows us to, this right here is our first introduction to what the heck a struct is. So what we did is we defined a struct named planet, and it has a variable named name, and a acceleration, and it has a function named gravitational force, which uses acceleration variable from within the planet struct itself, but also takes in a mass parameter so that you can calculate what the gravitational force is, and that'll return basically a decimal value. So then a way that you would mainly use this struct is to kind of declare it like a type of variable, which mind you, is actually quite similar to saying like int var int equals 1. In this case, planet, it's very simple. You just have to say planet equals, you have the type, so planet Earth is the name of that variable. Then say equals new planet, allows you to create a new struct instance that on its own happens to contain the name variable, the acceleration variable, and also allows you to call the gravitational force function right off the bat. So let's quickly take apart what the heck just happened. Again, the first line, public struct planet, is there to indicate that we are declaring a new type of variable named planet. I'll talk about what public means because that's something new that we have never talked about during basics programming. But for now, I'm just going to ask you to wing it and just skim over what the heck public means for now. We have two more lines that says public string name and public float acceleration. This declares that the planet struct, each instances of variables that is of the type planet, will have a name and an acceleration variable contained in it. So it's like a variable inception where there's a variable inside a variable already. Member variables, we are calling each of these lines right here, the public name and the public acceleration, we are calling these member variables, which are basically variables defined within a struct or a class. They're commonly used to organize a bunch of variables into a single group and or to provide data to methods that rely on them. So an excellent example is vectors. If you use Unity's own vector3, this is why I'm able to call vector3 type, because I'm using Unity right now, and like I said, it's a built-in variable within Unity. And I say forward equals vector3.forward. I'll go over what the heck forward stands for. It's a property, by the way, but we will go over what that means. When you type that in and you type in, forward.x, forward.y, forward.z. People who know their 3D geometry will probably recognize that basically this is a vector, a direction, indicating from the origin which direction this vector is facing towards. So the x direction, the y direction, and the z direction are the Cartesian coordinates of all three axes in the direction that it's going. They obviously can be positive, negative, these are all decimal values. And by putting that all together into a single vector type makes it easier to actually organize that information. It would be a lot more tougher to say, have variables called, float forward x, float forward y, float forward z. So rather than having all three variables and then, now having to rename a new set of three float variables for a new set of vectors when you want something like, say, back for each one. Instead, it's a lot easier to, this is me demonstrating how frustrating this would be in practice. Instead, what you could easily do is just say vector forward and then vector back, which is just forward multiplied by -1. It's the reverse direction of forward. And then, that gives you right off the bat a collection of 6 variables between just 2 structs. So again, that's one way of organizing, utilizing structs, to be able to use structs as a way of collecting a bunch of variables together. We also created a function within that variable within the struct called gravitational force, which of course is we're defining it as returning the gravitational force of a mass off of this planet, assuming that they're on the surface of that planet. I decided to take a shortcut because I did not want to write out the actual full gravitational force equation. So excuse my laziness, but this is what I'm choosing. And then, of course, the content of that function is simply to return the mass being a parameter that is defined by the user itself, and the acceleration, which is a member variable inside a struct. So you might think about, oh wait, you have Earth down here. Does that mean that you want to set the acceleration of this to 9.81 f, so that when you call the gravitational force, this will be the value that will be used? And the answer is, that is correct, hypothetical person I am describing asking that question. The very reason why you'd want to add in functions inside a struct isn't just to be able to collect those functions into a struct itself, but also to be able to utilize any of the member variables within that struct, so that you can create these libraries of functions. You can use these functions readily and more usably to get some valuable data out of it, or even to use the functions to manipulate the member variables themselves. So methods. Methods is just another name for a function. It's basically a subset of a function in a lot of ways. There are functions declared within a struct or a class that uses a member variable for its lines of operation. A lot of programmers tend to use methods and functions interchangeably. Pedantically, there is a difference. Like I said, methods are supposed to be structs or class methods that actually use member variables, versus functions which do not use member variables whatsoever. But like almost everybody calls them one or the other as if they're both the same thing. So I'm not going to be here to be a grammar jerk about it. So without further ado, yes. So methods. Note that the method gravitational force uses the member variable acceleration, which I just mentioned is one of the usefulness behind that. So it will use whatever acceleration happens to be set to during that moment. So in this case, we did set the planet Earth's acceleration member variable to 9.81 on purpose. Basically, we created a new type of value named planet, and we let the code know that it contains 2 member variables and 1 function, presumably to actually act like being able to calculate what it's like to be on the surface of that planet. So how to use this? As noted earlier, we use by using the start. So right under this void start function, we are creating a new planet Earth by using earth.name equals Earth, or you can also call it Aerith. I'm going to be a jerk because and cause a lot of flashbacks for Final Fantasy VII fans. Fun fact, real truth, Aerith from Final Fantasy VII is actually named As, or I think Asa, yeah, Asa in Japanese, which is meant to be Earth. So this is kind of an inside joke for me. Anyways, and then you can use this debug variable. You can use the recall the member variables by just saying earth.name, and then be able to use the function earth.gravitational force. So as an example, I can say debug.log planet name is. And then I can use string supports plus sign operations, and it does almost exactly as you would predict, which is it combines together whatever this string is with a value of whatever this happens to be. And then let's create a new line, debug.log gravitational force, Taro's gravitational force on this planet would be, and then I'm going to say Earth dot gravitational force. 150 is not my kilogram units, but we're going to pretend it's kilograms. And then when we run that, by just simply clicking the run button right here, whatever happens in this screen does not matter. You can actually see here in the console, let's see if I can bring the magnifying glass. Magnifier, perfect. Here. You can see that now we have planet name is Aerith. Taro's gravitational force on this planet will be 1,471.5 almost newtons. I have to be accurate there. It's not exactly newtons because we're in USA and I should probably grab an actual weight that gives me kilograms rather than pounds. 1.2. There we go. So now we'll know how much force I'm really experiencing. 3,000 newtons. Okay, good. So mystery solved. But yeah, what's important is that to be able to use any sort of, I'm sorry, I'm skipping over this. Oh. Yeah, that is a lot of newtons. 600, well, 700 newtons. All right, whatever. Too many mysteries solved in one day. My mind can't hold it. Anyway, so taking apart these lines right here, planet Earth equals new planet basically allows us to create a new type, which is planet, which is Earth, a new variable, which in this case we called it Earth. We gave the Earth's name variable, quote unquote Earth, and then the acceleration 9.81, which allows us to change this variable's instance of these variables. It's because remember, our Earth itself contains all these variables in and of itself. So then that allows me to set this planet name as Aerith and the acceleration as 9.81. Finally, these two debug lines right here. What I'm doing in this case is for Earth.name, I'm recalling, as in, remember each variable allows you to store and recall that stored information. I'm recalling Earth.name here, and I'm appending it to this text planet name is : Likewise, I'm calling the gravitational force function, which is this function right here, you can tell from the highlights. I'm calling the gravitational force function, which sets the mass to whatever the value 150 divided by 2.2 is. And then that value is itself being multiplied by acceleration, which is set to 9.81. That gives you the gravitational force of that value. Replace that, append that to this whole text that says Taro's gravitational force on this planet will be so on and so forth. So in summary, using a struct is very simple. First, you need to define the struct itself. What the name is, we called it planet right here. What member variables it contains, in this case we called it name and acceleration. What methods it contains, which in this case we called it a gravitational force. You can obviously add as many as you like. Same applies for member variables. And then all you have to do from there is we can create a new instance of it by using the new keyword. So it's here, planet Earth, new planet. Simple enough, and we can modify any of those member variables and call those functions as necessary to actually utilize that struct. So in this case, Earth.name, we're calling on the member variable to actually be able to store the word Aerith. We're doing the same thing for acceleration, except this time with the value 9.81. Probably this will be useful for other planets. What's another planet where we know the acceleration value of within the surface level? Venus. Yeah, what's the acceleration value for Venus, seeing that that's supposed to be... Right, I know. That's what... Mars is what? I mean, yes, you'll be very heavy because of the atmosphere, but that's besides the point. Mars, what was the acceleration for Mars? 3.8. So then we can easily replace this Earth with instead Mars. And then when we run that, now it says planet, oh, whoops, magnifier. Whoops. Now it says the planet name is Mars and the gravitational force that I'll face on the surface of Mars is 260 newtons. So many mysteries being solved. All right, so that's kind of the joy of being able to use structs. Like I said, it allows you to organize these informations, and if you want to like replace those values really quickly, then you just have to change the name of that variable and call it a day. Note that to access an actual variable inside a struct or a method, you just have to add a period right after the name of that variable. Most IDEs like Visual Studio will all correct that and provide you a list of options that you can choose. So in this case, we have Mars.name. So if I type in Mars and then I say period, then it's going to give me all the possible, these little blue icons right here tells you what those member variables are. When you declare a struct, it will come in with its own built-in functions as well, whether it be toString or equals. But the important part is we defined a function called gravitational force, and thus it allows us to actually declare that. It allows us to pull in the parentheses to see what the full text of that is supposed to read. So yeah, we have planet Earth, we have Mars, we have Venus. So far, so good. Yes.
It's 8.87. Chris looked it up.
Great, awesome. So exceptions. Structs cannot be defined within a function or method. So it does not make sense to declare a struct inside, this is a function right here, void start. So if I try to say, public struct superplanet, whoops. You can already see this red squiggly line, and if I hover over it, it'll say like expected something else. This is basically Visual Studio complaining that you can't declare structs inside functions. That's just not acceptable. Structs can be defined anywhere else, however. It can be defined within a namespace, something that I'll talk about in advanced programming. It can be defined within any class or structs. So you can actually define a new struct right here, public struct new acceleration, and then public float super acceleration. And then notice that it's not complaining. So that's totally okay to do. You can also declare outside of the class struct, or the class files itself. So just on its own, if it's just hanging around, that'll be perfectly acceptable. So those are all places where you can actually declare a new set of structs. It's worth noting, okay. Best practices, most of the time you'll want to define structs in their own file. So rather than this setup that we have right here, it's actually better to do this. Oops, I lost it. Okay, there we go. It's actually better to do this. And in fact, if I would personally recommend it, I would actually create this planet into a new file called planet. But I'm going to leave it like this for now. So why put it in separate files? Structs will still be accessible in other files So if I were to create an entirely new script right here, let's say similar to last time, I'm going to add a component, new script, and then we're going to say other script. So aptly named, create an add. Let it think for a minute. Open other script. So here's other script. Well, whatever. Because I declared it outside of test struct, if I were to use planet right here, so if I basically copy and paste this, it'll work just fine. However, if, like last time, I instead move the planet inside the test struct itself right here, then what you'll notice is that after a while, it's going to come up with red squiggly saying what the heck is going on. And if you hover over it, it says the type or namespace name planet could not be found. Are you missing a directive or an assembly reference? That is true. What you'll actually need to do is, because planet is declared within test struct, the class, you'll actually need to say test struct dot planet, and that resolves that problem. So all instances of these planets need to be replaced with test struct. So rather than having to write that over and over again, just generally speaking, it's easier and more relaxed if instead you just declare it in its own separate file like this and call it a day. That's just a problem with scoping. That's every programming language basically scopes anything between two brackets. So seeing that the struct was originally declared within the open brackets of test struct earlier right here, that meant that it scoped planet's existence within test struct itself. Whoops. So again, this is a good practice. This is not so great practice. There are reasons why you want to do this, but long story short, most of the time you don't. So good, not so good. Okay, so let's talk about public. What the heck does public stand for? Well, public happens to be something called an access modifier. And I'm going to talk about two different extremes in access modifiers, public and private. There are actually a couple of different access modifiers, but what is an access modifier at all? Access modifiers define where a variable, method, struct, or class can be accessed. C# has 5 different access modifiers. I actually had to research this as I discovered there was more than 3 as I originally assumed. In order of permissiveness, private, protected, internal, and public. We are going to completely skip internal and protected internal. That requires talking about namespaces, and I am sorry, that is not within the scope of this story, this class right here. So instead, I'm going to be talking about private and public, and then we'll cover protected in part 2 when we actually talk about inheritance, where that actually starts mattering. For now, what I would argue that you should assume is that a lot of these act in a lot of ways like private. And then public is just, we'll find out what actually public actually means. So access modifiers are usually declared in front of a declaration of a variable or in front of a declaration of a class or a struct. So as a perfect example, here's a public right here. It's been written right before the word struct. Another public right here, written right before the word class. Void, usually for functions, you would write it before what the return value of that function is. So public, float, then finally the name of function, so on and so forth. You can replace any one of these with private. Actually, I would recommend doing that and finding out what happens. Long story short, you're going to get a bunch of errors. See? Errors. So we'll worry about that, why the heck that happens. So public. Public makes any variable, methods, whatever, accessible basically anywhere, everywhere, so on and so forth. So remember, as you might recall, if I moved public struct planet into here, then other script complained that, you know, planet does not exist, that you needed to write down test struct.planet. Well, the fact of the matter is, it still lets you actually access the definition of that planet itself. So I'm just going to, for sake of demonstration, make sure that we have test struct here. However, if I were to switch that public into private instead, I don't think this file will complain. Yeah, this file will not complain. This file will. And it'll say, well, why the heck are we getting red squigglies? It says, your test struct.planet is inaccessible due to its protection level. The access modifier, private, basically prevented planet from being able to use outside of test struct. So generally speaking, public is a fairly safe assumption to make. Again, it makes it accessible anywhere, regardless of where the code is. You just have to make sure you have all the namespaces and the classes, embedded class names, and so on and so forth defined. So here's an excellent example of public string name being accessible right here. Since name right here is public, that means that test.name here is also accessible. However, if you use private, private makes any variable, method, etc. accessible only within the colons or the curly brackets that they were defined in. So as a reminder, curly brackets restricts the scope of the variables, methods, etc. Variables in particular stops existing once past the trailing closing bracket. So in this case then, going back to public struct right here, so if name exists within this bracket, but I did make it so that it's accessible if you declared any of these planet variables. But if I were to change this name to private instead of public, now what you're going to see is a red squiggly under names because the access modifier claims that it is supposed to be private and thus not accessible outside within this range. Similarly, if I were to do private right here, since the planet is declared within this semicolon, it continues to the planet continues to exist within these two semicolons right here. But if I were to move this to update, then it won't complain about it. However, past this semicolon, especially in other files, then planet just ceases to exist. And then it says that you can't access those anymore at all. Well, ceases to exist is incorrect because it clearly recognizes it exists, the error conditions. But what's more important is it cannot be accessed outside of those brackets is what is the more important part. So it's almost as if, you know, its existence completely disappeared after that. So in this case, we're setting the string tag to private. It's accessible within any methods here, public void print tag, because private here is declared within this this curly brackets and this curly brackets. So it can exist so long as any functions or member variables are trying to use it within these two curly brackets, which print that tag apparently does. However, the moment you start trying to use it outside of that, then it starts complaining. So an equivalent of this will be something like, say, doing, well, I want to keep doing this. So an equivalent of this is doing something like, say, acceleration. If I were to set that to private, this line is not going to complain because acceleration, again, is declared within these two curly braces. But it's not declared within these two curly braces. It's already ended right off here, and so, you know, its accessibility ran out or ceased to exist outside of this ending curly braces. Default access modifiers. Technically speaking, access modifiers are optional, so your code will still run if you don't say public. However, different languages does different things with it. So here's what I researched on C#, and I hope I'm correct with this. For variables, methods, functions, properties, and constructors, it will default to private. So this right here, it's as if we've declared it private. String name and string float acceleration as private, and the rest of the lines will act accordingly. This is not true for Java. Java looks a lot like C#. So if you're trying to learn that and you completely forgot to put the access modifiers, it does not do the same thing, which was a shocker for me. So long story short, a good idea for any language is to actually define the access modifiers from the first place, because whatever the default acts like depends on the compiler or the language. Usually the language definition itself, but sometimes the compiler, because whoever wrote the compiler was being a jerk. For structs and classes is a lot more complicated. So this is technically possible too. You don't actually need to write public, but a lot of weird stuff happens, and I don't exactly fully understand what happens with this. So we're not going to discuss about it now. Again, long story short, it's a good practice to make sure you add in your access modifiers regardless. Access modifiers. You do not need to define access modifiers within a function itself, because there's no reason to. If it exists within the function itself, then it only exists within the two brackets, and so there's really no reason to do that. The compiler will complain anyway, saying, what are you doing? There's no reason to do this. So here I have a function. If I were to type in public newtons equals mass times acceleration, semicolon, it's going, oh, this should be a float, public float newtons. It's going to complain because there's really no reason why this float, this public should be in there. If you remove it, then it's happy. And in this case, whatever access modifier newtons is really does not matter, because it's only going to exist within this function. And then within this function, you can't define structs and classes anyway. So it's meaningless on top of more meaninglessness. So that's why that exception exists. Good practices in regards to access modifiers, especially in context of structs. While C#'s default access modifiers are actually pretty darn good, they act more or less like what most programmers would expect. It is still recommended to define access modifiers for readability. Also for the fact that different languages has different ways of doing things. Java, for example, is really weird. Default does not act like public or private or anything else. It's really weird. So just generally speaking, it's a good idea to define that at all times. Variables should, member variables, that's not just variables right here. Generally speaking, member variables should always be private unless they're programmed to never change. We will talk about one instance of how you can program a variable to never change. But generally speaking, if you have member variables here, which we have 2 demonstrations of, you should actually make these private. There is a long explanation as to why that is. Many of it kind of historical, but also many of it still practical to this day. For now, what I'm just going to say right off the bat is just trust us. If you have a variable, if you have a member variable inside a struct, set it private. There are a lot of really good reasons not to make it public. So here I'm showing what a good practice is. Need to access a variable, create a public method, function, or property instead to allow you to actually set and get that variable. Likewise, structs and classes should almost always be public unless they're embedded within another struct or class. So in this case, we have a planet struct that is actually embedded in the class right now, but if you are declaring it outside, if you are declaring it outside of any sort of classes, it's always a good idea to set that to public instead. Excuse me. I should probably get rid of these now that I'm going to continue with this design pattern. If structs or classes happens to be embedded within another struct or class, opinions tends to vary by that. I would recommend being pragmatic and figuring out what the scenario is for that. The good idea of when you want to use privates, generally speaking, is when you don't want anything to access it. As a rule of thumb, my personal favorite method of dealing with whether to declare something to be private or public is to set everything to private first and then worry about setting it public later. Exceptions to this obviously being, if a function needs to be accessed outside of that and it's obvious that it's meant to be, then you set that public. If most of the time classes and structs are public anyway, so leave that as they are. Opinions also tends to vary on whether to make methods, functions, and properties by public or private. Again, play it by ear. For making private variables accessible within Unity Inspector, declaring a variable as private and use serialized field attribute is usually the best way to do that. For those not in the know of what the heck I'm talking about, why is it complaining? Oh yeah, okay, that's to be expected. Give me a minute. For those not in the know of what I'm talking about, when you go to the Unity Inspector, right now you're not seeing anything under test struct, but you can actually declare something as public int var int equals 5. If you say public int and then you switch back to here, once Unity compiles, you'll notice that under test struct, anytime now, did I declare that at the right place? Yeah, it should be appearing. I wonder why that doesn't work. I guess they changed it so that that doesn't happen anymore. Oh, here it is. Never mind. I don't know what the heck happened. Anyways, as you can see right here, let's bring the magnifying glass. Magnifier, magnify this. There we go. So you can see right here under the inspector, it now created a var int 5, which allows me to change that variable to any sort of value that I feel like. And in turn, that will actually change this var int variable when the game actually runs. This is great, but as noted earlier, this by definition is a member variable. It's within a class right here. So normally then a good practice is actually to set it to private, but doing so that makes var int disappear completely from the inspector. So how do you keep it appearing in the inspector? Well, C# has attribute, I'm going to comment that out real quick just to kind of demonstrate that this is not going to show up. There we go. So var int disappeared from the inspector. But if you want to make sure that it stays within the inspector, you can use the serialized fields attribute to make sure that it pops up right here. Thank you. So here it is, var int, shown up right here in all of its glory. Yay! Okay. So with that said and done, so consider that we have this struct bank that keeps track of transactions. Oh, so this is me providing a reason as to why private is a good idea to keep. So this is my example of, let's say we have a bank, struct bank, that retains a balance. And you were to say, oh, balance, change the T-bank balance to T-bank balance plus 10. But some sort of error occurs and the balance is all wrong. How do you keep track of the bank transactions that are happening? Well, one thing you could do is add debug.log on every line the transactions are happening. So for an equivalent of that is me going like, all right, so I could go to debug.log earth.name, and then, debug.log Mars name, so on and so forth, but that was really long and tedious and not really worth the effort, especially if the bank is being used all over the place. Another thing that we could use is instead using something called a property. So C# has this convenience factor called properties, which are basically getters and setters of a variable. So let's fix struct planet. Right now they have public member variables. We're going to change them to private member variables. And furthermore, for the heck of it, we're also going to change the name of those member variables to use underscore. Fun fact, I don't know why Microsoft allows you to use underscores. Oh, and it's going to complain about this. Yeah, let's change that to underscore as well. So you can use underscore for whatever reason as a start of a member variable. I do not agree with this. It's not a good idea to do this, but whatever. It's just one of those features. And then after the member variable declaration, what we can do is we can declare something that looks like this. So let me actually type that out. Let's say public. Remember, functions and properties can be of any sort of access modifier for whatever practice you want to reflect. But in this case, we want to be able to access names. So I'm going to create a property called a name. And then all it's going to do is on its getter, it's going to return underscore name. And then on its setter, it's going to set name to whatever the value you set it to. And likewise, we're going to do the same treatment for acceleration. Public float, because acceleration variable is a float. Acceleration get return underscore acceleration, and then set underscore acceleration equals value. So now you might notice, yes. Huh?
Why are you against underscores as a number variable name? Is that your personal preference?
It's a personal preference. Here's an excellent example as to why. Planet cannot have an instance property. Oh, that's just. So here it is. This is me declaring an integer variable, 1 equals 1. It just looks terrible. Like, that is all sorts of horrifying code that I've ever seen in my life. So, like, it makes sense that you can't do this, because the first letter starts with a 1, and from there it just assumes that what follows is supposed to be either a number or maybe even an F to declare it to be a float, that kind of stuff. So this makes sense to me, but like then you have this and you're like the fact that it allows you to write that kind of really bad code to me is bad programming language design. But again, that's me being opinionated. So yeah, that's the reason. For the purpose of obviously doing this presentation, I'm using underscore anyways, because we can't call this name. Otherwise, it's going to confuse, the program will confuse itself between, well, which is it, right? And here, the problem it's saying is the type planet already contains a definition for name, which is true. We already have a definition right here called name, and there's an ambiguity. So here we want to use underscore name and make sure that that doesn't happen. Make sure that that problem gets resolved. So anyways, as you can notice, by doing this, we've removed all the errors from here. Recall that before that, when we added any of these in, I'm using a quick shortcut here. Before that, when we added these in, it complained that name and acceleration didn't exist. Now it does. And so basically, by creating properties, it allows you to, properties itself allows you to treat this as if it's a variable rather than a function that requires you to pull in parentheses. A function like here that requires you to actually define parentheses. So like here or like here. So what are properties? It's a C# exclusive feature. No other programming language I'm aware of has this. That creates two methods, a getter and a setter, that syntax-wise acts like a variable. Taking it apart, every property starts by declaring at least a type of the property as well as its name before the opening curly braces. Optionally, an access modifier is prepended as the beginning first word. So under public string name, we're declaring a property named name, and the line above indicates that the property name is a name, it's public, and it returns it's supposed to be treated like a string. Within the properties brackets, you have to write in either a get, set, or both to be defined. So in this case, we created a get under name. And then here, under acceleration, we also created a get and a set. Hypothetically speaking, we could get rid of the get. Off of acceleration, we'll get no problems in regards to how it's being displayed. So what does get stand for? When you declare a get, you're declaring a getter of that name. So that getter then has a content of return underscore name. So the getter will act like a function. It will act as if you've called earth.name parentheses. And then within that parentheses, within that bracket, it'll basically throw in this content return underscore name under that function. You can add in as many lines as you want under this actually. So for example, if I wanted to be a complete jerk to everyone, I can say name, no, I control the planet name. So then when I actually run this code, right here where it says planet name is Mars, if I run this, it'll say planet name is no, I control the planet name. So like I said, this is getter, anything inside a property actually is just another function. Since the property name is declared as a string, it returns a string name underscore n name because that's what return underscore name does here. If a set is defined, a new variable value is created that one can use to modify its value. And in this case, value is set to whatever is left of that. So as an example here, what does this value stand for? Well, it depends. On this line, it will be set to Aerith. In the next line, it will be set to Mars. In this line, it will be set to Venus. So whatever happens to be where the equal sign is set to, that is what value will be set to, and then you can use that value variable as any way you like it. So again, I can also be a complete jerk and say, ha 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 ha. And if I do that, where it sets the value to ha 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 ha, then the value in turn is being used to name, because value is just another string variable. Again, right here, whoops. See, it's saying now ha 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 ha. So yeah, really, like I said, it's just a function that has a very specific purpose of either setting or getting a specific variable. Using properties, basically you use it like any other variable, earth.name right here. The second line above the name's set. The second line above calls the name's set property by changing the variable value to earth and setting it to the member variable. So basically it's setting, this above line is saying under .name into the variable .value, changing the value to earth, and then value in turn is setting it to underscore name member variable. So then the above line calls the name's getter property, which is right here, return name, and then it just returns the underscore name member variable. Quick note, basically behind the scenes in C#, what it actually does is it creates a few new methods called get underscore name and set underscore name string value. So any references to those name properties gets immediately replaced by these two methods. That as a quick test, I think if you actually try to say public string get underscore name, it's going to complain. Okay, apparently I'm not. Yes, it did. Type planet already reserved a member called get name with the same parameter types. So I was correct. It literally just replaces the get property with get name. So if I were to actually declare this below the name property instead, it's going to complain about the function at the function declaration. Or maybe not, it just complains at the property itself. So, but yeah, this literally just replaces name with this function get name. So this, whoops. So this right here and this right here is exactly the same thing in C#. It's just used different. It's just outside of the context used differently. Cool, I didn't know that. Also remember that property can be defined with get only or set only. These will be treated as either read only or write only respectively. So if there's only a get only, then that makes it read only. If it only has a set, so this is write only, this is read only property. And it'll even indicate as such on the errors if you actually try to use it incorrectly. Lastly, there are actually shortcuts in making properties. You could just say public string name and then say get set if you don't want to use any variables. So as an example, I could say public string nickname, and then I can say get and set. And it will just act as if in all the other stuff right here. It just acts as if it's another variable, member variable that you just declared, or like another property that you just declared. I believe you must say get and set because you can't say get only or set only. It doesn't know what to do with those. All right, so then this allows me to segue nicely to constructors now that properties are over. We haven't really went over what constructors are, so let's actually talk about it. Constructors are basically functions that allows you to, a method, excuse me, that allows a programmer to initialize a variable before it's actually being created, or at the same time that that variable is actually being created. Almost all programming languages supports this feature, and a lot of them actually requires them. C#, you might notice we don't have any constructors in here. This is a big no-no from what I understand with Java and C++. You must declare a constructor in both of those languages. C# just automatically creates one for you if you don't define it. Huh? Oh, okay. I believe C++ will not. It actually requires you to. Right. And constructors are really simple to define. You just say public, then planet, planet being the name of the struct itself, and then parentheses, let's say string new name, float new acceleration. And then we can use new name and acceleration to the name of the property, new name, acceleration, new acceleration. And there you have it. You might notice that earlier it looked like it was trying to complain about something right here. That's because struct requires you to define all these member variables, which is very nice of the compiler to do that because you want all those variables to be defined because you didn't define them with anything. Also worth noting, struct does not let you do this. Temp. It does not let you declare by default. And I believe struct does not let you define default constructor either. A default constructor is any constructors that takes in no parameters. So here, so even if I were to do this, yeah, it will still complain because structs cannot contain a parameterless constructor. There's a long story behind as to why that is. I'm not going to go over it. But just to let you know, if you run into those errors, that's the reason why. Constructors can shorten these 3 lines, the planet Earth, to just 1 line like this, to new planet Earth. I just demonstrated that. In fact, by creating this new planet right here, I can now replace all of these. Oh, well, nickname is not important anymore. I can now replace all of these constructions. Remember, again, C# will automatically create default constructor if you haven't defined it. We can now replace these with just this. So now we don't need these 2 lines anymore, and we can do the same thing here. 3.8f. 8.87f. And what that will do is it will use this construct. Whoops, let me use a handy dandy Visual Studio feature. Haha! Okay, so split screen. So what that will use is, it will basically use this constructor right here because you declared it with 2 parameters, the first one being the string and the second one being a float. So it will say, do we have a constructor right here that uses a string and a float? And here it is, it's under the planet. So we're like, okay, that's what we want to use. We'll replace new name with the first parameter, Earth, and we'll place new acceleration with the second parameter, 9.81, and we'll set that to the member variable's name and acceleration. So effectively, we have achieved almost exactly the same thing as before. So here's me talking about all that changes I did, taking it apart. A constructor is always declared with the same name as the struct itself, and optionally starts with an access modifier. So you could potentially take this out. There is not a good reason to do so. I personally would recommend defining it as public almost all the time. There are some scenarios where private would make sense. Actually, there's not a good scenario where private would make sense. But generally speaking, you want to make sure that there's an access modifier declared on the constructor itself. Unlike a method, even though this declaration looks like a function, unlike a method, the type is not defined because there's no need to. It will always return a planet. So we don't want any ambiguity. We want to make sure the struct returns a planet right off the bat. And then in this case, the constructor is declared with 2 parameters, the first one starting with a string and the second one being a float. The content itself, it's basically taking the parameters and assigning the member variables, simple stuff. If a constructor for a struct is defined, all member variables must be assigned. I've already mentioned that problem earlier. That says the initial value does not have to come from an argument itself. So if you wanted to, you could write another constructor right here, and I'm going to take out the string name, and then here I'm just going to give the name null, because you might remember strings can actually be null, and then that just works as well. And if you want to say, now if you want to create a new mystery planet, and then you don't want to give it a name, but you do want to give it an acceleration, that allows you to use this new constructor right here with that only takes in the float. Yeah, that's basically it. So even though all member variables must be set, they don't necessarily have to be set by an argument within that constructor itself. And again, structs are not allowed to have constructors that have that has 0 arguments. So why is this useful for structs? Arguably, constructors helps organize the code so that, you know, you basically have to write less lines to initialize all the information on that code. But there's also one more benefit that exists. And this is something that I think a lot of people who use Java are familiar with. But there is a feature in C# called read-only, which allows you to turn a member variable to become a permanent value that can never ever be changed except in the constructor. So the sole exception is that read-only variables can only be inside in a constructor exactly once. After that, their values cannot change at any point in time. So remember that all constructors must define read-only variables exactly once. So as an example, we took out all the weird ones. So anyways, yeah. So as an example, we can turn in here private name to read-only. Read-only basically stands in between the access modifier and the type. So now when I say read-only name right here, we're preventing anyone from actually changing that name. So one of the errors that we will actually be getting is right here, name. Why is it complaining about that? Because underscore name is a read-only variable. It cannot be assigned anywhere else outside of a constructor. This property is not a constructor, and thus it's complaining that this cannot be allowed. So again, we can take that out. By doing this, basically we're forcing the name to be read-only and must be declared within a constructor itself. After that, you know, you can't touch it. This is actually a really good example of where having a public variable does make sense. So as an example, I can have a public read-only integer ID variable on the planet. What that means is all of these must now define the ID for this planet. ID equals ID, and likewise here, ID equals ID. And then it's complaining that none of these values have it, so we're going to say 0. Oh, wait, this is the third planet from the sun. Mars is the fourth planet from the sun. Venus is the second planet from the sun, although that is not the reason why that is not the only reason why it's super hot. And there we go. So I added in the ID because we wrote 2 new constructors that requires the ID, but also here we're setting the ID to in the constructor itself, which is allowed, but outside of that we are not allowed to change that. So if I were to write here inside a function ID equals 0, then it's going to complain that ID is a read-only value and it cannot change. Again, for Java programmers, this probably sounds familiar because the word final does exactly the same thing in Java. So yeah. Whoops. Did I skip all the way to the front by accident? Oh no, here it is. So read only. After that, just use a variable like any other, just with dot period ID. Remember that you can't change its value though. So the first line is valid. The second line right here, earth.id equals 5, is invalid because it's set to read only. A constructor shortcut, you could define 2 constructors to make providing an ID value optional, or just use this to define other constructors to shorten the code. So that's a good thing to quickly mention. I did actually define these, but if you're being lazy and thinking to yourself like, oh, I don't want to change any of these right now, then potentially what you can do is you can, for one, basically copy and paste this, and then set ID to some other value like say 0 if you want to, or you can just get rid of all of that and say this 0 new name new acceleration. And what this will this side of things, I like to do this personally. What this thing does, holy crud, I need to come up with a new name for this. What this open parentheses does is that it will basically call this constructor and run it through with the parameters that you give in here. So in fact, I could actually add that same shortcut in right here as well with this ID null as the name and then new acceleration, and then get rid of all that content, and that would effectively achieve the same thing. And since I'm still getting an error at the bottom there, I probably need to create a this where ID is 0 and a new acceleration is provided, and then we take out the int ID. There we go. So that basically achieves the same thing. It's shorter to write, just to let you know, that's an option. This is actually important later down the road in part 2, but for now I'm just mentioning that this is possible. Take it or leave it, I don't know. I find it easier to write. It's not necessarily easier to read, however, admittedly. And you know, because none of these need content anymore, I might as well just like do that and call that a day. So yeah. Oh, whoops. The 2-argument constructor above, we used this basically 3-argument version of it and toss in all those variables. Notice that when you're doing that, all the read-only declarations where it says ID equals ID is considered normal, because the way this operates is that it gets called on creation before it lets you do all these other things. So if I were actually to try to change ID after this to 5, it should complain. Okay, it does not. I guess it's because it's still within the constructor phase, so that's the reason why. So yeah, that's this shortcut. And then we're going to talk about object-oriented programming a little bit. Just a tiny little bit, because it's already 8:34. I did plan this lecture to be hopefully shorter than 3 hours, which we're getting pretty darn close to achieving, so I'm happy about that. Objects. So this is going to be mostly hypothetical. There's probably going to be no code in regards to this except one. But objects does a lot of really cool things. I'm sure a lot of you heard about it. What you just got a glimpse right here, in fact, is object-oriented programming. This right here, all this code about us declaring a struct, all its member variables and its functions and its properties, more functions being used outside of other classes and so on and so forth, declaring using new and whatnot. This is actually all object-oriented programming. Object-oriented being the idea of organizing where all your functions, properties, and member variables are into a single type, and then being able to reuse it like they are right here as if they're planets. So, I mean, the way we're kind of treating Earth, Mars, Venus is objects, and then the way we're treating planets is a structure of that. Or if you're using the word classes, classification of that. That's actually what class is short for, classification. So if you might have noticed, in regards to defining this struct right here, I'm going to use this. In defining struct right here, by itself, struct doesn't actually do anything. It's just a declaration of a new type of a variable. It's only by using that variable, creating a new instance of that variable type, are we actually able to use any of the information that is stored within here. That is, generally speaking, the terminologies that we like to use is we like to call structs and classes as their name, structs, and here is a class right here. This is a class. But if we started using, you know, the Earth variable, the Mars variable, the Venus variable, once we declare them using a new, then we like to call those objects because they are objects of a struct. They actually contain variables inside of it. This is something that almost every programmer agrees on and do not use interchangeably. So to be absolutely clear, if we're using the word object, we're using that term not in regards to defining a class, we're using that very specifically as an instance of that class, but it is a very generic term per se. So yeah, that is one thing that most programmers will in fact be pedantic about. But yeah, you know, here planet is just a struct. It's a definition of what the variable planet contains, but in and of itself contains no data. Earth is an object because it contains data, the ID being 3, the name being Earth, and acceleration 9.81 as a type of object type planet. So why object-oriented programming? If you couldn't tell, that almost every popular programming languages under the sun allows you to group all these information into these classes and structs. But there's actually more to it. By upgrading from structs to classes, we use structs in this case. And I mentioned earlier, I'm just talking about structs this time around because generally speaking, it's easy to use. It actually behaves just like any other variable does, which I'll explain what I mean by in part 2 when I say that. But in the meantime, if you're using these new planet kind of things, be told that it acts like it would be expected. The moment you start upgrading to classes, those variables start acting very strangely, and I'll go over that again in part 2. By upgrading from struct to classes, though, outside of variables starting to act strangely, they can also unlock a lot more new fancy features. These include pointers, interfaces, inheritance, abstracts, and polymorphism. Those are just a couple of features that I can think of at the top of my head. Holy crud, there's a lot more features that are available in classes, but for us to talk about that, first we have to talk about how to upgrade from classes, structs to classes. It's actually super simple. See this? Change struct to class. You did it. That's how you upgrade to classes. So this right here, I can upgrade to just class, and you have exactly the same thing done. So everything that you just learned about structs, with the sole exception of a couple of random restrictions that structs have, is interchangeable with classes. So how you write a class is exactly the same way as you would write a struct. It's super simple. You can easily transfer between one or the, you can easily transfer from struct to classes by simply changing that word. The same is not true the other way around. As a classic example, if I were to change this to a struct, I will get complaints. Yep, right here. Why is up to part 2. Yeah, it's a cliffhanger. Like I said, there are a ton of features on classes, and I am sorry, that in and of itself is another lecture entirely. So this is why it's split into 2 parts. I wanted to make sure that we know how to write a class at all. And as you saw, how to write a struct for that matter at all. And I thought that this would be really useful information for being able to use that. But yeah, for part 2, we're going to talk about all the other super useful features that classes provides us, as well as other gotchas that makes using classes slightly more complicated than you would with structs. But other than that, any questions? Cool. But yeah, I hope you all stick around for part 2 because there are actually a lot of really good reasons why you want to use classes over structs. It affords a lot of really good new features. But I'm not going to lie, it's a lot of content. So, and I'm also not going to lie, pointers in particular is a very strange feature of classes. And like I said, it acts like a gotcha. Structs does not have pointers. If people know exactly what I mean by that and have not heard of structs before in C#, now you know. They're value types. I hope the magnifying glass worked. On the stream, I mean. tune in for part 2. Okay. That's good. Huh?
Is it still streaming?
Yep. Cool?
Chris is asking me to play music.
No. Well, if that's it, then that's it for me for part 1. I hope that information is useful for everyone. It'll be a lot more useful when I actually start talking about classes, but just to let you know, everything that I talked about applies to classes as well. You can write classes in exactly the same way. The only exception to this is the struct exceptions, especially in regards to the constructors. You can define default constructors in classes. You can define initial variables inside the member variable declarations itself. And what was the last thing? I think that's it. Those are the two weird exceptions that structs have that classes do not. Yes, I'm done. All right.
Thank you very much for the start.
No problem. I apologize that this is a two-parter. I am sorry, it is a really dense topic. And I'm sure once we get to part 2, you'll realize, oh wow, that's why. No, I think I'm good for now. We shall close the stream in 3, 2, 1.